All right. So I guess we'll go ahead and start. There we go. All right. So this is the FRC Java programming session. We're going to cover command-based programming and the simulator. I am Andy Gosser, the presenter. I've got Brandon Gosser here with me as well. He's a team member from 7028. He's going to be just helping monitor the chat and answer questions as we go along. I've been a programming mentor for 7028. This is my 4th year, and Brandon is a senior at St. Michael Albertville High School, and this is his 4th year in FRC. He's the programming lead for the team. So here's what we're going to go over. We'll first talk about the life cycle of a robot, and we'll cover command-based programming and then the simulator. So right now we have a poll question. If the moderator could put the first one up. What is your experience with Java programming for robotics? Are you able to put that poll up? Paulina, are you there?
Yeah, I'm there. Sorry.
All right. Oh, it looks like maybe our poll didn't. Oh, here it is. I don't know how to. There we go. I guess I can do it.
Yeah.
There we go. All right. So I think both poll questions are up there now. What's your experience with programming robots with Java? And then have you used the FRC robot simulator? Give me just a minute to respond to that. All right, it's looking like we have quite a few people who are new to programming and they've heard of the simulator but haven't used it for the most part. A few people who didn't know there was a simulator. A few people who have done programming in other languages or Arduino and Blocky, even one that did FTC. So looks like we've got quite a bit of difference, probably more on the side of not having experience with Java programming robots. So that's good. All right. So this session wasn't going to go too much into getting started with Java programming, but we can cover that a little bit more, and we'll have time for questions at the end, and we can definitely open up to any questions you want to ask at the end. Just close this poll window. All right. So this is the life cycle of a robot when we're programming. When we first turn the robot on, it's in the initialize state. So in initialize, we can get our program started, connect all of our sensors, connect our motors, get everything wired up. And we're not allowed to move the robot, but we can do anything we need to do to get it ready, get all the sensors reset and everything. Then once it's done initializing, it will automatically move into the disabled state. So like in that photo there, our robot's sitting there waiting for the match to start. It's in the disabled state. So for the most part, you won't do anything except when you enter the disabled state. Maybe you'll stop all of your systems. You could put like lighting effects into the disabled portion where you have a light strip on your robot or something and then it flashes, but you're not allowed to do that during the event. So it would turn off once the robot was enabled. And then during a regular FRC match, the first portion of the match is autonomous. And during autonomous is when your robot drives itself without anybody interacting with any controls. So in a regular match, we would then move into the autonomous mode. The robot will automatically move there when the match starts. And then that's where your autonomous programming will run. If you're going to try to drive forward, you're going to try to deliver a hatch panel or throw a ball or whatever the game happens to be, you would do that during that autonomous period. And the robot could go back to disabled if you emergency stop it or If the event ends prematurely or something, it could move back. But the normal flow would be for then to then move into teleop, and it'll stay in teleop for the remainder of the match. And that's when you would use your Xbox controller or your joystick to drive the robot around. You can still use autonomous functions during that time, but it would be teleop operated. So maybe you have some buttons that control certain autonomous functions. And then once the match ends, moves back to the disabled state. So we can program our robot in a few different ways. The way that I think works best, especially for autonomous, is to use command-based programming. And that allows you to break down your code into simple pieces that can do tasks. So your main robot code can deal with coordinating work instead of the details of what actually is getting done. So an example would be walk forward 3 feet. That would be a command that you might give. You know that you need to walk forward, but you don't have to worry about telling your body to put one foot in front of the other. So the command would be walk forward, where then a subsystem would deal with the actual walking. We'll talk about subsystems in just a little bit, but you can also create command groups to do more complex tasks. So that's where you might say walk forward 3 feet and then turn to the right. So you could then walk forward and chain those commands together. Maybe even you're gonna turn on a light switch. So the command would be walk forward, turn on the light switch, and you wouldn't have to worry about the details of getting that work done. Then subsystems, they encapsulate the basic functionality. So how you get those tasks done, but they shouldn't deal with doing the interaction between the different tasks. So the actual subsystem would deal with how to walk. So the command would tell the robot walk, and the subsystem would do the walking. So the reason that we want to separate those is that we don't mix that code together, and we have that ability to have a subsystem just deal with the things that it needs to know about. So if it's a drivetrain subsystem, it knows about the motors. Say maybe there's 4 motors, 1 for each wheel. It knows that there's motors that make the robot drive forward and turn. It knows how to make the robot turn and drive forward. The commands can then just say, I need you to do this work, and then deal with when is that work done? How do we figure out if we've gotten there? How do we put those commands together into more complex tasks? So it allows us to separate our code out. And then the command scheduler is something that's built in to the WPI Lib framework. The WPI Lib framework is what we write our robotic programming in for FRC. So we use Java, but then we use this WPI Lib framework on top of that. And that provides all of our functionality for how to interact with motors and basic running of our robot. So the command scheduler actually runs our commands. So you build the commands and then the command scheduler runs them. Commands use subsystems, and the command scheduler will make sure that you only have one command using a subsystem at a time. So an example that actually happens in programming is we've got the drivetrain and you want to teleoperate it. So you want to use an Xbox controller to drive it around. But maybe you have a button that you can press that puts the robot into an autonomous function. So maybe it's gonna shoot the ball, for our 2020 game, and you need to align your robot drivetrain in order to shoot the ball. So when you're pushing the button, the command to shoot the ball takes over the drivetrain to position the robot. So now your controls don't work on your Xbox controller anymore to drive it while it's trying to shoot. And then when it's done, you get your controls back. The command scheduler will take care of that for you so that you don't have 2 commands trying to use the same subsystem at the same time. So now we'll jump into a little bit of code. We'll go look at Visual Studio Code and how we would actually write a command-based robot. So this is Visual Studio Code, and it is what we use for WPI Lib programming. This session doesn't cover too much of the high level, but we can go into it just a little bit because there were quite a few new people still. So WPI Lib is what you would download and install on your computer that you're going to do programming. And it comes with Visual Studio Code, Java, everything that you need to write robot codes is in that one installer. So when you open it, this is what it looks like. And then there's a little button up here with the little W on it for WPI Lib. And you can push that and it'll open up this.
Here's a quick note. You forgot to share your screen.
Oh, is it not sharing that? Shoot.
Yeah.
All right. Thanks for telling me. There we go. Now can you see it, Visual Studio?
Yeah.
Yep.
Great. All right, so we'll start over. This is what Visual Studio Code looks like. We've got this little W button up here at the top. When we press on that, we'll get a list of functions that we can run. The keyboard shortcut for that as well is Control-Shift-P, and that will open up a list of all of the functions that we can run, WPI Lib or not. So to create a new robot program, we would click on that and then choose WPI Lib, Create New Project. And that brings up a little project creator window. And we're going to use an example. You can use an example or a template. If you go look on their documentation, they have detailed information about what each of the examples does, or you can start with a template just to get you going. We're going to use an example. We're using Java. And then here's a list of all the examples that they provide. We're going to look at a couple of these today, but the traditional hatchbot is the one that we'll look at right now. So this is their example of a 2019 robot, where the 2019 game is what's actually right behind me in my background, where we had the hatch panels that you could place onto Velcro, essentially, to hold the balls in. So this is a command-based robot that can do those hatch panels. And we just have to choose where we want to save it. I'm going to save it right there. Oops. And then create a new folder for the project, and I'm just going to call it hatchbot. And our team number is 7028. You want to make sure you enter your correct team number here, because that'll affect whether you can run the robot or not with your setup. And then I'm going to check this box for the desktop support. I won't necessarily need to do it right now, but for later when we want to run our simulator, we do need to have that on. So I'm just going to turn that on right now. All right, so it created the project, and then this window down here is our terminal, and we can see that it's doing some work right now. And there's also a little spinner down here indicating that it's doing some work. So we're going to wait just a minute for it to do the work. We should get a message that says build successful. That means it successfully built our Java code. And so this is a good place to watch if you're having any kind of problems, and you can scroll it up and down. So sometimes you'll get an error message and it'll be scrolled off. So you have to scroll back up. We also sometimes get little pop-up notifications in the bottom right. There aren't any right now, but it'll tell us things that we need to pay attention to. So it's a good idea to look down there as well if you're having any problems. So I think it's almost done building. Right. There we go, build successful. So that's what we want to see down there. We're happy to see that. So then our main code is under this SRC folder for source, and then main Java. And under here we have a FRC robot package and a few different things. This main class, if you've done Java programming, you may be tempted to come in here and change it, but for FRC programming, we don't do that. We actually leave this alone. It uses this robot base to run in our robot class. So we never actually edit this. So robot is our main class here. And I'm going to close this window down here. We may notice some of these, the life cycle of a robot that we talked about. We had init, and then we had autonomous, and then we had teleop. So this robot class gives us places where in that life cycle, we can run code when we enter that life cycle over and over again when we're in that life cycle state, and then when we leave that life cycle state. So we can, when we enter teleop, we can run some functions to get our Xbox controller set up, get our motor set up. Then when we're in teleop, it'll run teleop periodic over and over again. Every 20 milliseconds, it'll ask us, what do you want me to do? What do you want me to do? So that's where we would put our code for what we want to do over and over again in teleop. And then there's disabled as well, that when you enter that new state, we can disable that. All right, and then robot container is where we set up our subsystems and our commands. So we'll create them in these other folders, the commands and subsystems, but then robot container is where we do all the work to get everything connected together. So this is usually gets to be a fairly large class. This is where we put a lot of our stuff. So we'll take a look at the drive subsystem. So we talked about a subsystem being the one that knows about how to get the work done. So here we can see we actually have some motor controllers. So this is a robot that it was probably a tank drive, maybe had probably 6 wheels on each side because the Indy Mark drivetrain is what a lot of teams use, but 2 motors on each side to drive those wheels. So there's a left motor group that drives these 2 motors and a right motor group that drives these 2 motors. And then this built-in differential drive class is one that we can use where we can give it a right side and a left side, and it will know how to drive the robot when we tell it to drive it. And then we have encoders on the wheels as well that tell us the positions of the wheels. And so the drivetrain subsystem knows about that. And then we can, from the outside of this class, we can just ask it to arcade drive, which is, we tell it a forward motion and a rotation. So you can think of that like driving on an Xbox controller where the left finger joystick makes the robot drive forward and backward, and the right one makes it turn right and left. So that would be an arcade drive. So then this class automatically would say, okay, I want you to drive forward and I want you to rotate. That means I need to drive the motors in this way. So a caller from outside doesn't even know how many motors there are or how the drivetrain is set up. The subsystem knows that. So then we've got some commands, just taking a look at my notes here. We've got this one called drive distance. So that would be like we talked about, where we want to drive forward a set number of inches at a given speed. And so this command takes care of doing that for us. So each command has a life cycle as well. It'll run an initialize when it first starts running, and then it can have a periodic. This one doesn't, but it can have a periodic where every 20 milliseconds we have some work that we want to do. And then there's an is finished, and that gets called after every periodic cycle to ask your command, is it done yet? And then once it's finished and you've said, yes, it's done, then this end command will run and you can take some action. So if we look at this one here, we're in the constructor, we're saying how many inches do you want to drive, how fast do you want to drive, and what drive subsystem do you want to use? And then we just hang on to those up here. And so then in initialize, we reset the encoders. So the encoders are what's on the wheels that tell us how far the wheels have turned. So we want to say start at 0 and then start driving the drivetrain forward at the speed that the caller asked us to drive. And 0 is the rotation. So we're just driving straight forward. So it'll start driving and initialize. And then every 20 milliseconds, the WPI lib scheduler will call us and say, are you done yet? Have you reached your distance yet? Is what we're going to try to figure out. So we look at how far have the encoders turned. The get average encoder distance takes the 2 and then averages them. So sometimes your robot won't drive perfectly straight. So it averages the 2 is what they're doing here. And then we want to make sure that it has gone at least the distance that they asked to move. And this one uses absolute value. Just in case you use this example and when you drove forward, your encoders turn backwards, that can happen if you don't have them set up exactly right. So this uses absolute value to see, has it moved that distance? And then, so once this returns true, then the command scheduler will call our end function and we stop the robot, arcade drive 0, 0. No speed, no rotation. We want to just stop the robot. So this demonstrates where the subsystem knows about the motors and how to drive, but it doesn't actually do any driving. And drive distance knows how far you want to go, knows how to make it start and how to make it stop, but doesn't actually know about the motors or how to make them turn. So that's really what we wanted to see here. And then the other thing we talked about was that you can take multiple commands and put them together into a command group to make an autonomous function. So their complex auto is an example of that. It's a sequential command group, which just means I want to run commands one after another. You can also do things in parallel, and you can come up, with some more complex stuff. Like in our example, maybe when you're walking toward a light switch to turn it on, you can walk toward the light switch and raise your arm at the same time, right? That would be something that you want to do in parallel. And then when you reach the light switch and your arm is up, then you want to turn the light on. So you can do things like that, but this one's just a simple sequential. So it's going to drive forward a set distance at a set speed. Once it's reached that destination, then it will release the hatch panel. So however the manipulator works to push the hatch panel onto the Velcro and release it. And that command knows about that, but we don't know about that here in our group. And then it's just going to drive backwards that same, or a backup distance, it's going to drive backwards. So it's driving up to that hatch panel, releasing however the manipulator works, and then moving back. So this is just an example how you can stack those together in a sequential command. All right, we'll pause right there just to see if anybody has any questions with this part so far. If you want to either send them in the chat or unmute yourself and just ask, and then we'll look at the simulator next. All right, we'll move on to the simulator here to get my sharing set back again. Okay. All right. All right, so the simulator. It looks like not very many people had experience with the simulator. Some people didn't even know it existed, which it's still relatively new. It did exist last year, but for 2020, they're adding additional enhancements to it. So we'll just talk about what it's supposed to look like in 2020. So this is a view of what the simulator looks like with the 2020 field loaded into the 2D field view. So we'll do a demo and we'll see that in a little bit more detail here. So what can you do with a simulator? You can test your code without a robot or a robo-Rio, which I think is probably going to be especially helpful this year when a lot of us are working remote, don't have access to a robot, but we still want to be able to write some code and run it. It has some built-in dynamics that it can simulate. So it can simulate the physics of an elevator, which is kind of what we have up here on the top right, this 3244, the Granite City robot. They have an elevator here that can lift up so that they can reach up to these higher positions. So there's a class built in that can simulate gravity and the weight of your arm so that you can actually program that, or your elevator, sorry. And it can simulate an arm, which is our robot here, that 7028 robot has an arm on the front that raises and lowers. The physics of that is a little bit different because as you reach the top, you don't have gravity pulling on it. And then when you flip back, the gravity pulls backwards. And as you come down, the gravity is heavier. So there's a class built in that can simulate arm gravity. There's one for a flywheel, which we've got a picture here where this is a flywheel that spins up to have a ball get shot out. So this ball loads up, this flywheel spins, and then it shoots the ball. So you can simulate the dynamics of a flywheel. You can also do a differential drive, which I think is kind of neat this year. You can have it simulate a robot differential drive, and you can put it onto a 2D field and see where it is in position. And then based on the stuff that you have running, you can have it also simulate battery draw. So it can show you how many amps does it think you're drawing, and does the RoboRio still have enough power with everything that you're drawing. In addition to those new dynamics that you can do this year, you can also look at motor output. You can have it simulate encoder positions. So you can really run stuff in the simulator. One big limitation to the simulator, though, is that it doesn't simulate a lot of third-party hardware. So if you use the across-the-road electronics, Talon SRXs, or Falcons, or even the Spark Max, the stuff that's built into those motor controllers, we can't simulate that. So that's definitely a downfall, because if you have a real robot, you can't necessarily pick up that code and run it in the simulator. So you might be able to test some of your commands and your subsystems, but others you might be limited on what you're able to do. So we'll just jump in and actually take a look at the simulator and some code. You see my Visual Studio? All right. So we're going to do another one from an example. So we'll push the little button up here. We will create a new project. And we're going to do another example. And let me look at which one we want to do. The ARM simulator. So we're going to do Java and then the ARM simulator. Save it right there. I need to make sure to check this box. Actually, I'm going to not check that box just to show you how you can turn that on if you forgot to turn it on. So we'll generate our project. And then if you forgot to turn that on during initial setup, you can go into this command group up here and type in desktop, and there's a change desktop support enabled setting. You can check that, and it says it's currently false. We're going to go ahead and enable it. So if you forget to check that button, or if you want to simulate on some code that somebody else created, that's how you turn it on. So in mine, I need to change this just slightly. They used a joystick, and I don't have a joystick. I have an Xbox controller. So I need to use an Xbox controller instead. And then right here, we're going to change this to get a button. All right. Do that, and then we'll build it while I talk. All right. So this is an example that simulates an arm like we talked about. And so we can actually just launch the simulator. So I'll push this. Let me make sure my Xbox controller is connected here. I think it didn't connect. Oh, there we go. All right, looks like it connected now, I think. So we'll run the simulator. We just run simulate robot code on desktop. And then we'll build it and run it in the simulator. And this little pop-up will happen up here. You have to make sure you watch for that and select this first one, the HalSim GUI, and then click OK. If you accidentally click outside of that or don't select anything, the simulator won't launch. So then you just have to stop it with the stop button and try it again. All right, can you see the simulator? Yep, okay. So we've got a bunch of different windows in here. Some of them, they all overlap when you first start, so you have to do some shuffling around a little bit. But the robot state is the one that usually will come up here, and you can move your robot into those different states: disabled, autonomous, teleop. Not sure if I can zoom this and make it a little bigger for you guys. There we go. And then test mode is another mode we didn't talk about. That's something you can run your robot kind of in a bench test mode. You would never use that during a real competition, but you can use that as well in the simulator. Then you have your digital inputs and outputs. These would be the DO ports on your Robo Rio. It'll tell you what is the state of those. Our code doesn't use those at all, so they're just grayed out. You've got the PWM outputs. That's the pulse width modulation output if you're connecting your motors into your controllers using PWM. So this would be our motor output, essentially, in this example. And then we have encoder positions, which is the position of our arm. So we'll put that one right there. And you get a little FMS data, the field management system. So if you have to get any game-specific data, you could put that in here. So that would be like in 2019, the example behind me there, you had to know, was your robot on the blue side or was your robot on the red side? Yeah, the game specific was 2018. In 2018, there was an elevator and a switch, and it was randomized which side, whether you were going to deliver your stuff to the right side or the left side, and you got that information in game specific data. So if you have anything that the FMS is supposed to tell you, you can put that in here. And the Alliance station is here, where you would say, am I in position 1, 2, 3, and then red or blue. So that would be for like 2019. All right, so then the joysticks, this was a little weird, and it took me a while to figure out how it works. So there's two windows that give you joysticks. The system joysticks shows you all of the joysticks that are connected to your computer, and the joysticks shows you what joysticks you have in what positions. So we have to take our system joystick and drag it into the joystick box. So I know in my code, I used joystick 0, and I've got one joystick, so I need to drag it in there. And because I'm using an Xbox controller, not a joystick, I have to check this map gamepad box. That I didn't find documented anywhere, and it really tripped me up, and I had to reach out to the WPI Live people to get help with that. So make sure if you're using an Xbox controller that you check that. So now you can see all the axes and everything, and as I move the Xbox controller around, we can see, and the buttons on the bottom there, the triggers, everything lights up as I push them. So now we can actually simulate something. We can put the robot into teleop mode. And this example was that when I push the A button, it should move our arm to a set position. So when I push A, we'll see our PWM changes. That's our motor output. And as I release, it goes back to 0. So this code will give extra power to the arm to raise the arm, and then as it approaches its position, it'll slow it down, and then it needs to hold a certain amount of power to hold the arm in that fixed position so gravity doesn't lower it. And so as I do that, we can see our encoders are moving, and our distance that they've traveled is changing, and our output is increasing in our PWM output. So this is just an example that shows using a button to move an arm, and so you can try out your code to make sure that you can program your arm. So that one's kind of exciting. I thought the more fun one was where you actually see the 2D field and drive the robot around. So we will create a new project again. Use an example, Java. This one is called State Space Drive Simulation. Save it there. That. And as soon as this one's ready, we'll go ahead and just launch the simulator. I think this one works. Yeah, so here's an example where something popped up on the bottom right, and we need to pay attention to it because I told it to run the simulator and it was already building. So it told me you can't have two WPI live tasks happening at the same time. So when it finishes the other one, it may or may not run the simulator, or it might just sit there and then I have to push it again. So yeah, I can just close that and then run it again. But at least it told me what happened and why it couldn't run it again. So pay attention to those. All right, so then we'll run the GUI. All right, so we've got the simulator again. This time we're going to use one of the other windows that we have in here. It's the 2D field view. I'm going to bring that up, and I'm going to just kind of, I think I'm going to just close a bunch of these. So I can make this one bigger and see if I can zoom this a little again. All right. So this is a top-down view of where we're telling the simulator our robot is. So it's right now in the bottom. It's actually outside of the field because the center of our robot is the position. It's at 0, 0. We can also go into the, not the settings, into here, 2D field view, and we can choose a background image for our field. And this is where I have a field that I downloaded from the internet, and I can put my field in there. And this one was kind of to the right size. It's pretty close. It's a little bit off from what it's got here. And so then to use our joystick, we have to find that system joysticks and drag it into our joysticks window. Check map gamepad again. And then this example that they put together uses the ability to drive a trajectory. And we're not going to go into that really in this session, but there's a lot of great information on the WPI Live documentation and a lot of people that worked on it last year on Chief Delphi. Great place to get help and find examples. So when we turn on autonomous, the robot will actually go and drive, and it'll drive like over to here. So I'm going to turn it on. We'll see it goes, drives up there and stops. So you can simulate, what your autonomous function is doing. And while that was running, we would have been able to, if I had the PWM window open, we could have seen as our motors were moving and our encoders, everything was moving. But I think it's cool to actually see it moving around. And then I can also use my Xbox controller and drive the robot around on the simulator. It's kind of tricky because you can also drive right off of the screen. But you can kind of simulate your code driving it around in teleop as well. You can put your own robot picture on that as well to drive it around, which is kind of neat. Or if you're trying to see, is your simulation going to work, to get the right part of your manipulator to the right position. If you have images to scale, you could get a pretty good visual, whether it seemed like it was working. So we'll go take a little look at the code that they actually have in here to make that work. Because you have to add in some special stuff to make the simulator know where you are and how things work. So in our drive subsystem, somebody asked, can you interact with game pieces? No, I don't think there's any way to put game pieces or even interact with the field elements. It's just a picture. I don't think there's any way to do that in the simulator right now. All right, so in our drive subsystem, we've got our motor set up much like we had before and a differential drive. And then we have our real encoders set up here, and we have a gyro. And then differential drive odometry is part of what is used to be able to run those trajectories. So we'll just kind of skip over that. What we're interested in here is these simulator classes. So this is some special code that has to be in here to make the simulator work. We have the differential drive sim. That's the class that simulates the differential drive. Then we have the encoders, our field 2D, and that's the class that we have to tell where do we think we are on the field. And then that makes the images for us. And then they also had this sim double for the gyro, which we don't necessarily need to look at. So odometry is this class. That's the one that will keep track of where our robot is on the field. That's outside of the scope of this, but that's how this class works to be able to run a trajectory. We've got a bunch of stuff in our drive subsystem to update odometry to know where we are on the field. And then those simulator classes are set up here in the constructor at the bottom. The encoder simulators need to take the encoders. The drivetrain simulator takes a bunch of parameters. So if we hover over it, we can see what some of those parameters are. Oops. So we have to give it some information about, this is what are our drive motors? How do they work? What's our gearing? What's our track width? The radius of our wheels, a bunch of that information so that it knows how to simulate where our robot is and how it functions as it rotates. So then there is a new see, where was that? It was in the where we were. There's a simulator periodic. Here we go. So periodic runs in our subsystem every 20 milliseconds, just like any other periodic. For 2020, there's a new method called simulation periodic. And that one will run periodically, but only when we're in simulator mode. So any code that you put in here won't run when you're actually running on your robot. It'll only run in the simulator. So this is where we can put any code that we need to update the simulator or to simulate our behaviors. So first it sets the data on the drivetrain. So the trajectory class that we used, we tell that we want to drive a given trajectory, and it tells us how hard do you have to drive your motors at any given time. So in normal code, we use that just to run our motors. But in a simulation, we have to tell it this is, the simulated robot is actually behaving this way. So we have to tell the drivetrain that here's what our outputs are going to be, and it's going to be what we were expecting our motors to be. So our regular code updated our motors to say, you need to drive this fast. We need to update our sim drive system to also tell it that it needs to drive that fast. Then our encoders, we simulate those. We basically just tell our encoders, you moved the position that we expected you to move to. So in a normal system, you might give it an update and say, between updates, I expect it to drive 20 ticks. In our simulator here, we're going to tell it, you were supposed to move 20 ticks. Part of when we construct our simulator, we can tell it, how much do you want to vary from that? So, because in real life, we're going to expect that our encoders move 20 ticks, but when we actually check it, it moved 25, right? So our simulator can throw in some standard deviation to make sure that our system still adjusts properly. And then we also update our gyro to tell it that it's turned in the direction that we expected it to be. And then this right here is how we make the robot appear on the field. We tell the robot simulator to set the robot's pose, and the pose is an XY position and an angle that it's turned. So that's kind of how it works. I think it's great that they have some examples in here. That's really a great way to go and run it and see how things work. One other thing you can do is set breakpoints. So I can set a breakpoint over here, run the simulator, and it'll stop right here. And then I can inspect what are the different variables, how are things behaving. The simulator is great for that. Sometimes that's hard to do on a real robot because you're right in the middle of driving and you try to stop, the robot keeps driving, right? The simulator will completely stop and halt for you to be able to check out how everything's working. So that is about it. We'll go back to the presentation. And we just have some resources here. We've got the FRC documentation link. That's definitely the place to start. Tells you how to use all of these things, how to get everything installed. And then we've got just 3 links there for the different vendor libraries too, Across the Road, SparkMax, and the NavX gyro. Any questions? I think we're just about out of time. We have a couple minutes. Oh, I think there was a question that we can have multiple subsystems for a single command. Yes, you can. That's part of when you construct a command, you give it all of the required subsystems, and you have to tell the scheduler which subsystems you require. So you can definitely take multiple, and it's not uncommon. Like in our robot for 2020, we had a shooter that shot a ball out, and we had an indexer that fed the balls in. Those two need to work together. When I want to shoot a ball, I need to spin up the flywheel, and I need to load the ball into the shooter. So it uses both of those. And then when that shoot command is running, we can't load a ball in from the back because it's taking control of that indexer. So you can definitely do that. Any other questions? Whether it's stuff that we covered here or any Java FRC questions, we can definitely take any of those too. See, somebody asked, does the programming software cost money? It does not. It's all free, and even everything is open source too. So you can go look at how it works, but it's all free. That first link that we have there for the FRC programming documentation, that will tell you how to get it installed and where to get the downloads. If you actually want to run a robot and use the driver station that we didn't look at here, you'll have to ask your team for the serial number for that. It's all included with FRC, but anybody can go and download the Visual Studio Code and the robot simulator. All of this is free, and you can install it on your machines at home and wherever and run it as well. It works on Windows and Mac for sure. They have some support for Linux as well, but not Chromebooks. Yeah, put the links in the chat, sure. The WPI Live, that's definitely the one to start with. And then these other ones we didn't really cover much of, but they're the vendor libraries. So that Phoenix one is great if you use Talon SRXs or anything from Across the Road Electronics. Definitely go there and look at their documentation. They have a lot. All right. Sure, we can show real quick how to add the vendor libraries to a project. So if I've downloaded the Across the Road Electronics and I want to use that vendor library, I have a Talon SRX on my robot and I want to instantiate the Talon SRX classes, I need to open up that command palette and choose Manage Vendor Libraries. And then if I've done the install on my computer from that link, I can say Install New Libraries Offline, and I'll get a list of the libraries that I have available. So I have the CTRE Phoenix here. I just select that, click OK. It'll ask me if I want to rebuild. I say yes. And then once it's done building, I should see there's a file in here that tells me what my libraries are. And now I can use those classes in my robot. All right, I think we're just about out of time. Any other questions? All right, well, thanks everybody. I hope you have fun at the next couple sessions.
Yep, thank you.
Thanks, Andy.